Hey, welcome to the 17th class meeting of EECE341, Introduction to Communication Systems. Today we start chapter 4. And the handout is downloadable. Homeworks will be assigned. And here goes the list of companion courses related to communications and networking. Next semester, you can take mathematics for electrical engineering engineers, EE engineers, A, and also introduction to digital communication and introduction to communications and network and introduction to digital signal processing. And even you can take graduate level probability and random processes. Especially this one will be offered as a full online course, so you can freely manage the time without being restricted by other courses. If you have any question related to these courses, please come to me after the class meeting. I will gladly explain what are these courses to you. Messages from me is very simple. Simplify and visualize. You will see these strange signs a lot today also. Simplify. Last time we finished linear modulation, and I'm not going to too much review, just I will list up the names. Since the content of the last class meeting was almost omitted from the exam, probably you haven't yet reviewed, but we talked about a pulse amplitude modulation, especially analog pulse amplitude modulation. There is a digital counterpart called pulse amplitude modulation, so be careful. Also, we talked about multiplexing in the frequency domain, time domain, and there are code domain, but we skipped that, and space domain. Also, I talked about the vocoder that was very popular for voice communication. And now the communication system's data rate is increasing. So you may say that, okay, just directly sampling and encoding the signal may be okay. Sometimes that works, but since the processes become so fast, still compression is very good for save the number of bits to be transmitted. Okay, here goes the preview. So some of you may wonder why the chapter 4 has title strangely. Logically speaking, if chapter 3 has linear modulation techniques, chapter 4 must have nonlinear modulation techniques. You are right. So let me draw this one. So this is the set of all modulations, modulation schemes, modulation techniques. And logically, as you imagine, we can divide it into linear and nonlinear. However, as you've seen already, even some of the modulation techniques in chapter 3 categorized as linear was not linear because it was the output, the modulated signal. The output signal was not a linear, didn't satisfy the superposition principle. For example, DSB with transmitted carrier, that requires a fine mapping of the message, which means that if the message signal is M of t, you not only scale it, but also you add some bias over some DC term. That DC term violates linearity. So precisely speaking, as we learned in systems theory, signals and systems theory, these modulation schemes called linear modulation was not linear. Okay, so this linear and possibly nonlinear was not a precise definition. Got it? And now, here, what is angle modulation? Definitely, it is not linear. The problem is that angle modulation, not always, but some of angle modulation techniques can be mapped to linear modulation. So there are two definitions. So this is mathematically precise definitions of linear and nonlinear. And this is just technically, so mathematically imprecise, technically accepted classification, nonlinear and linear. Got it? So later, probably if you take the communications major and if you carefully study digital angle modulation, you will be surprised to find that some of angle modulations are actually linear modulation. So the reason why is that people believe angle modulation is nonlinear in any sense, but actually it is not. Okay. Anyway, so this classification is a little bit vague, but mostly motivated by this approach. So here in chapter 3, what we've done was related to something like this. Some linear filtered version of DSP family. So let me, okay. So DSP signal is filtered. And DSP has two types, right? With transmitted carrier or suppressed carrier. So, and this DSP is related to some formula, looks like this. Here, the key is not just the amplitude is a time function. This phase deviation, angle deviation is constant. Got it? Now, what about the signals we are going to study in chapter 4? That is mostly something like this. So amplitude or magnitude is fixed, and we have nominal carrier frequency, and this is time function. What does that mean? If we want to modulate the carrier with message information, this contains the message. However, there are many ways for this theta of t function to convey the message. And among many different types, we will see two angle modulation techniques. And they are phase modulation and frequency modulation. So you may just regard that there is a modulation, a set of modulations called angle modulation, and angle modulation has phase modulation and frequency modulation as subclass. However, there could be other ways. But why these two are so popular? It is because when they started to use this angle modulation, at that time period, the hardwares will only allow these two, phase modulation and angle frequency modulation, viable. Other types, complicated operations on message symbols, was not possible at that time. But now we can generate any real valued bandpass signal. So this is important angle modulation schemes. But not all. They are not all, right? There could be other things. So currently, we can generate almost any signal in this form or in this form. Got it? So message may be somehow carried by this real baseband signal or that real baseband signal or amplitude as well as phase angle. If you take digital communications course, that is the story, okay? Your message not only affects xi of t, xq of t, or a of t or theta of t. However, that was not simple in the early stage of radio communications due to the hardware limitation. As I repeatedly told you, in order to just generate a radio wave using antenna, what do you need? You need to generate a very fast oscillating electrical signal. That was a challenge. And how can you multiply two electrical signals? So you just let the circuit to do some mathematical operation. That's not easy. And that was not easy. Got it? So initially, as a kind of nonlinear modulation, angle modulation was very popular because you just fixed the amplitude of the carrier and only put the message in the angle, phase angle, okay? However, currently, it is not the case. In digital modulation schemes, messages are not only carried by phase angle, but also carried by amplitude. And you will see the details in the introduction to digital communications taught by, that will be taught by Professor John Joseph next semester. Okay. So here goes the first page of new chapter. And as I already told you, this handout is based on our textbook written by Zimmer and Tranter. And this is based on the 7th edition. And I used the 2nd edition when I was an undergraduate student. So during last 30 years, the textbook has evolved. Of course, the 7th edition was currently the last edition, and it is almost 10 years outdated. So there have been a lot of new development. However, mostly this textbook is used as the introductory communications course. So it's okay, we believe. However, you'd better, in order to have most up-to-date knowledge, especially about the cellular communications or internet, probably you'd better take Introduction to Communications and Networking. Okay. And slides are mainly written by Professor Kyung-Chul Yang, and I modified a little bit. Okay, so here goes amplitude and phase angle in order to define what we are talking about. So as I told you, any real valued bandpass signal can be written in this form. Question. Given a real valued bandpass signal, is it unique to find A of t and theta of t? What is your answer? True or false? It's false. First, you can choose f sub c. So think in the frequency domain. Suppose you have some spectrum like this. Of course, this is, in general, complex valued conjugate symmetrical function, but just for convenience, I wrote as if it is real non-negative. Now, you may say that, okay, here is FC, but it's not true. You can choose some other value as f sub c. If you choose different carrier, if you choose, then you have different A of t and theta of t. Now, next question. Suppose you have chosen or you are given f sub c because in the transmitter, you used, for example, you have used some oscillator that has frequency fc. So you decided to use that one. Got it? So this is given. The question is it unique to choose A of t and theta of t? Again, it is not. Because if you restrict A of t as the magnitude or modulus of the complex envelope of the signal, then your choice of A of t and theta of t pair would be unique. However, A of t is not restricted to be a non-negative function. It could be positive or negative. Got it? And if you just change the, given a pair of A of t and theta of t, if you just multiply some arbitrary 1 minus 1 signal, then you can change A of t and you add and subtract pi, which means that theta of t is also changed. So your choice of A of t and theta of t is not unique, even if you are given fc. Got it? So be careful. One of my important message is that whenever you define something, think about existence and uniqueness. So here is another message. Got it? One of the biggest problem of Korean language and also Japanese and Chinese is that they do not have so-called article in Korean, 관사 or the on type thing, right? And also we rarely talk about plurals like 사람들, 사람, 학생, 학생들, 교수, 교수들. We mostly do not distinguish that. However, when you learn English and other Western languages, the article is one of the most important things. And that made a huge difference, I believe. Some people have written the book like Why the Eastern Asia, including China, Korea, and Japan, failed to do industrial revolution first. Okay, why industrial revolution occurred in Western hemisphere. And they talk a lot about that. But that book is written by Westerners. They don't know the language, how the language limits the imagination or cleverness of the people. The European language requires you to always think about whether I'm talking about something singular or something plural, right? But we don't do that. That makes a lot of confusion. Actually, even the Westerners sometimes made a lot of mistake without thinking about the existence and uniqueness. You may easily find the mathematician Pascal's mistake when he didn't carefully examine the uniqueness. Okay. So it's like this. When you define something, first, or you talk about something, think about the definition. And whenever you have definition, think about whether that thing you just defined exists or not. Sometimes we cannot prove the existence. We just believe. Then that's the cause of a lot of problem. And now suppose you agree that entity exists, but be careful. Next step is that you need to check whether it's unique or not. So whenever I talk about this existence and uniqueness thing, I tell you something like this. So no, I'd better not talk about this. Okay. Anyway, so be careful. That's why here I talk a lot about the uniqueness. Got it? So even though you have this formula, you have freedom to choose FC. Even after you choose FC, you still have freedom to choose AOT and theta OT. Got it? So this is not necessarily magnitude. Got it? So cross out this one. Okay. This is amplitude. Sorry. This is magnitude and phase. This is correct, but A is not necessarily magnitude. Got it? So let me write this way. No, not this. Got it? So from here to here, it's unique, right? Because this is complex valued baseband signal, and its magnitude is uniquely defined. And if you take out the magnitude, your phase angle is uniquely defined. Of course, under the ambiguity of 2 pi, integer multiple of 2 pi, that is ignored. So this means angle. So you may wrongfully think that, okay, this is the amplitude. I'm not saying this is true, okay? So this could be chosen as your amplitude, but not necessary. Got it? That's my message. As I told you in the introduction, in angle modulation, there are two most popular sub-modulation schemes. One is the phase modulation, and it is abbreviated as PM, and frequency modulation, abbreviated as FM. But not many people say this is AM because it's very confusing, because AM usually refers to the amplitude modulation, which refers to the specific DSB, which is DSB with transmitted carrier or large carrier. Got it? So even though we want to make an acronym AM to mean angle modulation, never do that. It will introduce a lot of confusion. In order to define what is angle modulation, let's precisely define some terminologies like angle, frequency, instantaneous frequency, phase deviation, something like that. Okay? So let's restrict, this is confusing. Okay. So this is not complex. Okay. If I have written all of these, probably I would have dropped this one. So suppose x of t is real bandpass signal. So this is real bandpass. And this signal has constant amplitude. So we have restricted. We are not thinking about general real valued bandpass signal. We are thinking about very special type of real valued bandpass signal that has constant amplitude. Then it could be written in this form, always, right? Of course, you have freedom to choose even f sub c. However, let's suppose we have chosen fc and have found phi of t. Then you may say that this is frequency, the frequency, but usually some person like me says nominal frequency. In Korean, 명목상의 주파수, but not often called it. But anyway, so FC is the frequency. But you want to name phi of t related to angle or phase. The problem is that this entire thing is called the phase angle, actually. And this phase angle of cosine function, okay? Phase angle of the cosine function or angle of cosine function, or some people just say phase of cosine function. It's very confusing. Sometimes phase, sometimes angle of the cosine function. In the context of angle modulation, is called instantaneous phase angle. Or some people call it instantaneous phase. Some other people call it instantaneous angle. It's very confusing depending on the textbook. But anyway, you understand what I mean, right? Because if you just view this signal purely mathematically, the argument of the cosine function is the angle or phase, or if you want, phase angle of the cosine function. But it's a function of time, so we need to introduce some quantifier that gives the idea of time. So instantaneous, which in Korean 순간 or 순시, is now the new name of this entire argument. Got it? So we have instantaneous phase angle. Now, this entire thing is unique if you have a constant amplitude signal, bandpass signal. Your choice of FC defines phi of t. So depending on your choice, actually, you have different frequency. That's not good. How can we have a unique definition of frequency? Some people, so do you understand what I mean? Suppose you have some quantity. Let's call it as theta of t. And one of you will rewrite it this way. One of you, will choose slightly different F2 and talk about this way, right? It's not unique. Even though theta of t is unique as the instantaneous angle or phase angle of this signal, you may choose F1 in your mathematical formula, right? You may choose different F2. In that case, you have different phi of t, phi1 of t, and phi2 of t. What is the frequency of this signal? So what you do is simple. We just differentiate this instantaneous angle or phase angle. And what do you have? You have 2 pi f1 and the derivative of this one. 2 pi f2 and derivative of this one. So if you divide by 1 over 2 pi, what do you have? You have this one or that one. And now they are the same because you have the same theta of t differentiated. Now we call this one as what? Instantaneous frequency of this signal. Okay. And this is unique. Of course, when I talk about unique, I already say it exists, right? Got it? So be careful in thinking about the definitions. Existence and uniqueness are two most important things. unfortunately, this is not much taught in even the undergraduate level education. I really feel sorry about that. So now you have defined instantaneous frequency. Because we have 2 pi 1 over 2 pi factored out, this has the unit of hertz, or sometimes per sec, or cycles, some people, they are all the same. Now, phase modulation. So I said there is an angle modulation that includes phase modulation and frequency modulation. Phase modulation has what? Has this, by the way, did I define phi only? Okay, that is wrong. Where is phi of t defined? Okay, so let me define this one first. By the way, phi of t is called the phase deviation. Okay. Now let me ask you a question. Phase deviation is uniquely defined? No, it depends on your choice of the nominal carrier frequency. So this is not unique. So let me summarize. So we have defined instantaneous phase or phase angle, that is 2 pi fct plus just theta, let me use theta, yeah, theta of t, and instantaneous frequency, that is defined as the derivative divided by 1/2, 2 pi, and angle deviation or phase deviation, or phase angle deviation if you want, that is defined as got it? So this is unique, that is unique, but this is not unique. Then what is phase modulation? Phase modulation in the transmitter, you usually have nominal carrier, so this may be well defined. This phi contains the message in the form of a fine mapping of the message. So as you see, the phase deviation is either this way, or if you want, you may add some non-zero constant. Got it? This may be better for the precise definition. Okay, so it's a fine function of the message. What? Phase or angle deviation is an affine function of the message. Got it? So it looks very similar to the idea of double sideband modulation, where amplitude A of t was proportional to, or was an affine function of the message m of t, right? So it's kind of very natural. What about frequency modulation? Frequency modulation has something like this. Let me not say it. Yeah, but actually we need this. Yeah. In frequency modulation, the message is an affine function. Sorry. The instantaneous frequency. See that? This is as I told you, this is what? This is the instantaneous frequency, right? And let me see. Just a second. Something's wrong. Just a second. P of t, deviation. Okay, yeah. So just a second. Where is theta? Sorry, theta. It's confusing. Yeah. This is instantaneous frequency, and instantaneous frequency is an affine function of the message. But as you already know, what is this one? This may be written as fc plus b of t dt, right? So since you have nominal frequency and this is affine, you may just say that phi is a linear function, or precisely speaking, affine function of the message. So do you understand? So this only is an affine function of the message. Then you have phase or phase angle modulation. If derivative of this one is an affine function of the message, you have frequency modulation. Why? Because derivative divided by 2/2 is instantaneous frequency, and frequency directly contains the message. That's why it is called frequency modulation. Got it? Is it clear? So now you distinguish what is phase modulation and what is frequency modulation. In phase modulation, phase deviation is an affine function of the message. And in the frequency modulation, you may say frequency deviation, because affine means you can take out any constant. Frequency deviation is an affine function of the message. Got it? Now let's visualize the result. So suppose you have a message signal, m of t, which is just the unit step function. So at time 0, t equals 0, you have a jump. So the value was 0 and suddenly it becomes 1. Now, this is unmodulated carrier. Now you modulate this carrier. Here modulate means you change amplitude or phase or both of this one by using phase modulator or frequency modulator. Now let's see. Here you see that suddenly the phase of the signal abruptly changes. Because here your phase deviation suddenly changes but become constant after change. So you have a sudden change of the carrier. Now, in the frequency domain, what happens? Your frequency is suddenly changing. So here, you observe the same frequency as the carrier, but suddenly at time 0, you observe higher carrier frequency. Right? So you have the difference. Now, I believe we have other figure. Yeah, here. So here goes another example. Suppose you have a sinusoidal message signal. So the value is higher here and lower here. And let's see what is the impact of this message signal at the output of the phase modulator and frequency modulator. This is a modulated carrier. Now, phase modulator has what? You see, suppose this is the reference time. Now, your phase increases approximately linearly and saturation decrease, right? So you see, it's hard actually. Visualizing and perceiving the message from the phase modulated signal is hard. For example, suppose I have removed this message signal and just have given you the modulated carrier and ask you, hey, draw the message signal using your brain. It's not easy. However, in frequency domain, it's much easier. See that? So here is your reference time, and see that the frequency here, you may regard it as a number of zero crossings within a unit time. Okay? You may regard it. Which means that number of zero crossings with the horizontal axis, time axis, right? So here, you see that these intervals reduces. So you have more and more zero crossings, right? So here you have the peak number of zero crossings. And the message value is at the highest value. And you have decreased the number of zero crossings. And further, and you have the lowest. Got it? So perceptually, frequency modulation is more appealing. It's easy to understand. And interestingly, this idea is used even in digital modulation. Once I told you a device called a pager, not phaser. What is a pager? So in the airport or in some train station, sometimes you hear announcements like this. 사람을 찾습니다. 포항에서 오신 김모 학생은 빨리 어디로 와주세요. That is called paging. Okay? And also pager has some popular name called 삐삐 in Korea. Okay? In 삐삐 or pager, they use frequency modulation for digital message transmission. What they do was very simple. They either transmit a low frequency signal or high frequency signal, to simply put. So if your received signal is the low frequency signal, then message bit is 0. If this is high frequency signal, then message bit is 1. Suppose, okay? Suppose this means 0 and that means 1. Now, you are asked to build a pager, receiver. What do you do? Okay, how can I detect the frequency or something? Actually, the manufacturers use the zero crossing counter. So they just use the zero crossing counter. So they counted number of zero crossings within an interval. And if it is greater than some threshold, the output was decided to be 1 and lower than 0, something like that. So this frequency-related modulation can be easily understood in terms of number of zero crossings within a period. Got it? Of course, it's a very vague idea, but you have that in mind. Okay? Anyway, frequency modulation is further divided by narrowband frequency modulation and wideband frequency modulation. And this classification is related to the frequency domain understanding of the frequency modulation. So a discussion will be deferred a little bit. First, narrowband modulation can be easily understood in the actually time domain, not necessarily in the frequency domain. The idea is like this. So first, we rewrite our real bandpass modulated signal as a real part of some complex baseband signal times complex sinusoidal signal. You know what I'm doing, right? Because we have a lemma or theorem U1. Real bandpass signal has a complex baseband counterpart or equivalent times e to the j 2 pi fct, if you want to add data. So we have angle modulated signal. So we have a constant and e to the j times phase deviation, right? This is phase deviation, phi. Now, suppose this phi of t does not change much, which means that it does not goes over 2 pi period a lot. It just varies a little bit. Then what can you do? We know from the Euler's identity, we have cosine phi plus j sine phi. And if angle is small, what kind of approximation can we make? First, cosine 0 is almost 1. And what about sine phi? We can further expand sine function using Taylor series. Or you can even say that, hey, this is well approximated by just the phi if phi is small. This is what you learned in your high school math, right? This is what you learned in high school, and this is what you have to understand for sufficiently small data in the college, right? So we wanted to talk about this one mathematically precisely. That is the equality involving the limit operator. So we can just rewrite this one in that way. See that? This one is written as that one. Now let's rewrite. And you have what? AC cosine 2 pi fct minus j, because of course this will give you j phi of t and sine, and jj multiplied becomes -1. So negative AC phi of t and sine 2 pi fct. Got it? And as you've just taken the midterm, this looks like something similar to what? Something similar to AM. In AM, we had what? We had something like this. What's the difference? We had cosine and cosine, or if you want sine and sine, or if you want cosine 2 pi fct plus theta and cosine fct plus theta. So we had unmodulated carrier that had co-phase with our message part. Now, they are similar, but there is a huge difference. See that? This may contain phase if it is a phase modulation. Derivative of this one may contain the message if it is frequency modulation. But in either way, this is angle modulation. And you see that message is contained here. And this is what? This is carrier, unmodulated carrier. So this narrowband FM, where phase deviation is very small, has commonality with AM in that it transmits unmodulated carrier. what's the difference? Unmodulated carrier has 90-degree phase difference between the part that contains the message. However, here, these two terms have co-phase, the same phase. Got it? Now, so far, this is in the time domain. Now, let's see why this is called narrowband FM, or sorry, narrowband angle modulation, or narrowband FM, narrowband PM under this assumption. Now, let's Fourier transform this one. Then what do you have? So this is Fourier transform. You have what? You have two direct delta functions for the carrier. And what? You have a message. So let's divide into one by one. What is this one? According to the Euler's identity, e to the j 2 pi fct minus e to the negative j 2 pi fct divided by 2j, right? From the Euler's identity. So, and the Fourier transform of this one, let's say that this is phi of f. So you have 2j and phi of f minus fct minus phi f plus fc. Got it? So this is the Fourier transform. And let's visualize this one. Then what you have is simple. The first two terms will give you delta functions located at your carrier frequency. And now what about this one? This is the Fourier transform of the phase angle shifted by Fc. So you have some signal like this. What if P of t is M of t? What will happen? This is nothing but the frequency translated version of your message signal, right? So if the signal is phase modulated angle modulation signal, then this signal has the same bandwidth as the DSP signals, right? So narrowband angle modulation has the bandwidth that is the bandwidth of this phase deviation. That is the general statement. And if this angle modulation is a phase modulation, then what? The bandwidth is the same as the bandwidth of the message, or precisely speaking, twice the bandwidth of the baseband signal. Got it? So this bandpass signal has the same bandwidth as the DSB family. Got it? And we don't know why it is called narrowband, because if this assumption is not satisfied, you will see dispersion of the spectrum over this bandwidth. So relatively, this signal under that assumption gives us narrower bandwidth. That's why this is called narrowband angle modulation. Narrowband PM, narrowband FM. Got it? So then what would be the wideband FM? This condition is not satisfied. Then you will see the wideband angle modulated signal occupies a lot larger bandwidth than ordinary DSB or amplitude modulated signals occupy. And here goes the lesson. So you know already that from the experience from riding your parents' old car that has still AM and FM radio receivers. If you find AM radio stations, the quality of audio is poor, right? And if you set FM stations, then quality is very high. Why? Because it occupies larger bandwidth. And as I told you in radio communication, what is the most scarce? Of course, it is subjective, but what is the most scarce resource in radio communication? Spectrum. So AM occupies just narrower bandwidth than FM. FM occupies larger bandwidth, and that larger bandwidth is not a waste. It is helping the quality of signal received at the same location, for example, with the same transmission power, much better. So usually we have a trade-off in radio communications like this. If you are not dumb, if your signal occupies larger bandwidth, you have something good. So what would be the good invention? Occupying same bandwidth, using same transmission power, but better quality. That is very challenging trade-off research. Anyway, time's almost up, I believe. No, that clock is too fast. It's 10:42, so I have 3 minutes to talk more. So let me see, what can I tell you? Okay, here goes a strange block diagram. It's conceptual. No transmitter, no transmitter looks like this. But just conceptually, let's distinguish the difference of the transmitter structure of the phase modulator and frequency modulator. Here goes the message. And it is amplified and serves as the phase deviation. And what is this one? I really hate, but anyway. And you have here AC cosine 2 pi FCT plus phi of t. Then what? You have phase modulation. Got it? Now, here is something strange thing. The message signal is integrated and used as the phase deviation. Why? It's because we define the instantaneous frequency as the derivative, where it is, derivative of the phase. So if this instantaneous frequency is an affine function of the message, then what is this phase deviation? That is integration of the message, right? That's why in the frequency modulator, we have this integrate. And integration is a very complicated mathematical operation, but from the beginning of the electrical circuit theory, we found a very good integrator called capacitor, right? So integration was not a difficult mathematical operation at the early stage of radio communication. So this is okay. And anyway, we need amplifier. Otherwise, we cannot generate strong enough radio wave. So this is okay. And you may wonder now, at this time, why FM dominated, not phase modulation, but frequency modulation. They are both angle modulation schemes, right? But why frequency modulation dominated? And that actually depends on the technology again. At that time, even though this looks difficult, but actually easier to build. Okay, what else can I add? Yeah, here goes the example. So in order to make everything simple, the authors of the textbook assumes, for simplicity, that message is a sinusoidal signal. So this is message frequency. And let's see what would be the output signal when we have narrowband assumption. Then, as you know, we have this one. And if we draw phasor, then here goes the difference. So this is for amplitude modulation, and this is for angle modulation. So if you're really confused, let me say angle modulation. Do you see the difference? As I emphasized, in narrowband modulation, the unmodulated carrier is not co-phase with the message. So if this is the unmodulated carrier, then that direction, you have the message. In the DSB, with transmitted carrier, you have unmodulated carrier, and here goes the message. And this part will be covered this Wednesday. That's all for the day.